Hi, this is your Professor Sudha Kolathuparambal, section 12.1 Testing Goodness of Fit. In this section, I am going to explain you how to find the critical values of the chi-square distribution and how to perform goodness of fit test. Hypothesis test for qualitative data, also called the categorical data. The tests are based on the chi-square distribution, which you learned in section 8.4. The test statistic used for these tests are called the chi-square statistic, and we usually denote by like this. Chi-square distribution is not symmetric, it is skewed to the right, and values of chi-square statistics are always greater than or equal 0. They are never negative. Now find the critical value of the chi-square distribution. So alpha is given 0.05 and 12 degrees of freedom. So in the row 12, that is the degree of freedom, and look at the column which has 0.05, and the critical value is found at the intersection of the row corresponding to degree of freedom 12 and the column correspond to 0.05. So that is 21.026. So critical value is 21.026. So this diagram represents the chi-square distribution with 12 degrees of freedom with alpha equal 0.05. So critical value is labeled here. So this shaded part represents the area to the right side of this critical value, that is 0.05. Now let's look at how to perform the goodness of fit test. Imagine that you want to determine whether a coin is fair. You could toss the coin a number of times and compute the sample proportion p cap of heads. That is the sample proportion. You could then use the test for a population proportion to test the hypothesis H naught equal null hypothesis P equal 0.05 versus the alternate hypothesis P naught equal 0.5. You learned that in section 9.4. The test for the population proportion is designed for the experiment with two possible outcomes, such as the toss of a coin. Sometimes we work with experiments that have more than two possible outcomes. For example, imagine that a gambler wants to test a die to determine whether it is fair. So the die has 6 possible outcomes, right? So 1, 2, 3, 4, 5 and 6. And if each of the outcomes are equally likely, then the die is fair. Assume the gambler rolls the die 60 times and counts the number of times each number comes up. These counts, which are called the observed frequencies. Observed frequencies. And assume okay, so these are the outcomes in this diagram, and these are the observed frequency which is given in this table. The gambler wants to perform a hypothesis test to determine whether the die is fair. The null hypothesis for this test says that the die is fair. In other words, we say that each of the 6 outcomes probability is 1/6, right? P1, let P1 be the probability of rolling a 1, and P2 is the probability of rolling a 2, and P3 is the probability of rolling 3, like that. Then the null hypothesis will be for all those which has the same probability, right? So null hypothesis will be P1 equal P2 equal P3 equal P4 equal P5 equal P6 equal 1/6. Alternate hypothesis says that it's not equal. 1/6. So in generally we can say, instead of writing P1, P2, P3 like that, we can say Pi, where I varies from 1 to 6, that is not equal 1/6. So now let's see what is the expected frequencies. To test the Gampler's null hypothesis, we begin by computing the expected frequencies. The expected frequencies are the mean count that would occur if the null hypothesis were true. If the probabilities specified by the null hypothesis are like a P1, P2, P3 like that, then the total number of trial is n. Then the expected frequency is E1 equal, expected frequency of 1 is, we can represent that as E1 equal n times P1, E2 equal n times P2 like that, and so on. So again, the expected frequency are the mean count that would occur if the null hypothesis is true. So now let's look at how to compute the expected frequencies for the Gampler rolling a die. So the probability specified by the null hypothesis are the total number of trial, n equal 60. Therefore, the expected frequencies are E1, that will be n times V1, so 60 times 1/6. E2 also will be 60 times 1/6. E3 also will be same 60 times 1/6. You are multiplying the probability by the number of trials. Okay, so all these will be equal to 60 times 1/6, that is equal 10. So that is the expected frequency. So the expected frequency for each outcome, we can write it as, the observed frequency of 1 is 12, observed frequency of 2 is 7, like that. That is the number of times each number comes up. And expected frequency is the mean count of that if the null hypothesis is true. If the null hypothesis is true, the observed and the expected frequencies would be fairly close. Larger the difference between these observed and the expected frequencies, stronger the evidence against the null hypothesis. We compute a test statistic that measures how large these frequencies are. So the test statistic is called the chi-square statistics and denoted by chi-square like that. So let's say, let K be the number of categories and O1, O2, O3 like OK be the observed frequencies, and E1, E2, E3 like that up to EK is the expected frequencies. Then the chi-square statistic is, we can write chi-square equal sigma and take the difference between observed and expected frequencies and divided by E. That means find the difference between these two observed and expected frequencies and square that and divide by the expected frequency for each one, then add everything together. And the degrees of freedom for the chi-square statistic is always 1 less than the number of the categories. So the degrees of freedom will be K minus 1. And this is under the assumption that the expected frequencies are greater than or equal 5. Meanwhile, there is no assumption on the observed frequencies. That means the assumption that the expected frequencies are at least 5 does not apply to the observed frequencies. Now let's look at the procedure for performing a goodness of fit test. So first state the null and alternate hypothesis. Compute the expected frequencies and check to sure that all of them are 5 or more. If they are, then you can proceed. Choose a significant level alpha and compute the test statistic. Find the critical value from table A4 using k minus 1 degrees of freedom, and k is the number of categories. If chi-square is greater than or equal to the critical value, we will reject the null hypothesis. Otherwise, we do not reject the null hypothesis. Then state a conclusion. Now let's look at this example on performing the goodness of fit test. So using the observed frequency for the die example, can you conclude that at alpha equal 0.05 level, the die is not fair? So the null hypothesis says die is fair. And alternate hypothesis says die is not fair. So first step is we need to state the null and alternate hypothesis. So we can state, okay, step 1, state the null and alternate hypothesis. So null hypothesis P1 equal P2 equal P3 and alternate hypothesis we can say sum or all of the pi differ from 1/6. Step 2, compute the expected frequencies. We compute the expected frequencies in the previous example. We found E1, E2, E3. All these we found by 60 times 1/6, that is equal 10. Which is actually greater than 5, so we can proceed. Then step 3, choose the significant level. So alpha is given 0.05, and in step 4, compute the test statistic. So the test statistic chi-square equals sigma O minus E square divided by E. So the category is 1, 2, 3, 4, 5, 6. And the observed frequency is 12, 7, 14, 15, 4 and 8. And the expected frequency is 10 in each case or each category. Then take the difference between that. So that is 12 minus 10, that is 2, negative 3, 4, 5, negative 6 and negative 2. Then square those values. So 4, 9, 16, 25, 36 and 4, and divide each one by E. So this one divided by E. So this one divided by this. 0.4, 0.9, 1.6, 2.5, 3.6, 0.4. Then add all these. You will get that equal 9.4. That means chi-square is 9.4, or that is the test statistic. So I'm going to copy down the test statistic. We found that we got chi-square equal 9.4. Next step, step 5, we need to find the critical value. So in the critical value, we need to find the degrees of freedom. So there are 6 categories. So 6 minus 1, that means 5 will be the degrees of freedom. So from the table, A4, 5 degrees of freedom and alpha is 0.05. So the critical value is 11.070. So chi-square is 9.4, which is less than 11.070. So we do not reject the null hypothesis. So we can conclude this by saying that there is not enough evidence to conclude that the die is unfair. If you are using a calculator testing the goodness of it, first press stat, then edit, then enter the observed value and expected value in L1 and L2, then press stat, calc, then select option D. For option D, if you want, you can press alpha and x power -1. That also you can use to select the option D, that is chi-square goodness of fit test. So G of F test. Okay. Then observe value, you can choose L1, expected value L2, degrees of freedom 5, then calculate and you will get the p-value. If p-value is greater than alpha, then we do not reject the null hypothesis. So first press stat, edit, and in list L1 we have all the observed values, and L2 enter all the expected values, then press stat, calc. You can use the arrow key and choose chi-square we need to select the test. Use the arrow key and select, highlight the test on the top. Okay, here. Okay, then use the arrow key. Okay, chi-square G of F test, then press enter, then observed values in L1, expected values in L2, and degrees of freedom 5, then calculate, highlight that and press enter. So you can see the p-value is 0.0941, that is greater than our alpha is 0.05, so we do not reject the null hypothesis. And you can conclude the same way how we conclude without using the calculator. So in this section you learn how to find the critical values of the chi-square distribution and how to perform the goodness of fit test.